So yeah, hopefully the problems in these worksheets will help you understand a little bit more these different concepts. So let's look at the first question that we have here. In this question, we are given a sequence, an equal to 1 over 2 roots 2 to the n, and we are asked if the formula for the given sequence is the sequence an, right, being strictly increasing since the ratio is greater than 1, or the sequence increasing since the ratio is less than 1, or if the sequence is increasing since the ratio is greater than 1, and so on and so forth. So basically what we are doing here, we are investigating the whether or not the sequence is increasing or decreasing, right? And right away, since we have already mentioned, right? So in this, I think there's a mistake in the question here. So basically, yeah, this question is wrong here. This question should be really use the ratio test, right? So use the ratio test to investigate whether the sequence is increasing or decreasing, right? Or decreasing. So that should be the actual question there. I think there's a mistake there. So, but anyway, so basically we have to use the ratio test to check whether or not the sequence is increasing or decreasing. So how do we do that? Well, we are given our sequence an, which is 1 over 2 root 2 to the exponent of n. Well, the ratio test tells us that we need to divide a of n plus 1 by a of n and check whether or not that is greater than 1 or less than 1. So immediately we know that a of n plus 1 is just the same as a of n, but you substitute wherever you see n with n plus 1. So we have 1 over 2 root 2 to the n plus 1 now. And using the concept of the ratio test, a of n plus 1 divided by a of n just gives us 1 over 2 root 2 to the n plus 1 divided by 1 over 2 root 2 to the n. And this is just 2 root 2 to the n divided by 2 root 2 to the n plus 1. Right? Now, right away you can see that 2 root 2 to the n is a common factor between the numerator and the denominator. So if we simplify that, we'll have 1 left in the numerator divided by 2 root 2 to the 1. Because remember, this is just 2 root 2 to the n times 2 root 2 to the 1. And since 2 root 2 to the n cancels with that, we are left with 2 root 2 to the 1 there. So that's the final answer. And we can clearly see that this is less than 1. Okay. So what does that tell us? Well, that tells us that the ratio is decreasing, right? It's decreasing, or rather the sequence is decreasing because the ratio is less than 1, right? So the sequence is strictly decreasing, okay? Because, and how do we know whether or not it's strictly or decreasing or just decreasing? Well, we know that n, all the values of n are natural numbers, and they are all starting at, I don't know, 0 to infinity, right? So to positive infinity. So all the values of n are positive, right? So we know that. Since we know that, we just know that as you increase the value of n in the denominator here, you will have a higher and higher value, which will get smaller and smaller than 1, right? Which will just be decreasing and decreasing, right? So as you increase the value of n, you decrease the overall value of a of n, right? Which means that the sequence is strictly decreasing and will never increase at any point, because n is just increasing, right? So since we know that, then we know that the function, or rather the sequence, is strictly decreasing. Okay, that means that the correct assertion here is 5. The sequence is strictly decreasing since the ratio is less than 1. Okay, so that's the correct answer. All right. So now moving on to the next question. We are given another sequence, an, which is equal to n plus 3 divided by e to the n plus 2, right? And we are asked to use the differentiation test to check which of the following assertions is true, right? Well, let's first take the derivative of the sequence, right? So we have an is equal to n plus 3 divided by e to the n plus 2. That means that the derivative of a prime of n is just e to, remember it's first the derivative of the numerator, which is just 1, multiplied by the denominator, e to the n plus 2, minus the numerator multiplied by the derivative of the denominator, which is just e to the n plus 2, divided by the denominator squared, e to the n plus 2 squared. Right? So now this can be simplified to e to the n plus 2, which is a common factor between the two terms in the numerator, multiplied into 1 minus n plus 3, all divided by e to the n plus 2 squared. Okay, which is further equal to, we can simplify e to the n plus 2 because it's a common factor in the numerator and denominator. Then we are left in the numerator with minus 2 minus n divided by e to the n plus 2, which we can clearly see is less than 0. Okay, so what does the differentiation test tells us about this sequence? Well, we know that the derivative a prime of n is less than 0. So if we look at the options that are given to us here, and how do we know it's less than 0? Because once again, n is increasing. Since n is increasing all the way up to a value very high, close to infinity, then we know that negative n is decreasing, right? So as you go from like n is equal to 1, for example, to n is equal to 10, you'll get lower and lower values in the denominator, which means that not the denominator but the numerator, sorry, which means that the overall derivative will be less and less than 0, right? So that means that we can, looking at the assertions there, we can already eliminate the first one, the second one, and we are left with 3, right? So now, what does the fact that the differentiation test shows that the derivative of the sequence is decreasing, what does that tell us about whether or not the sequence is increasing or decreasing? Well, we know that since the derivative is less than 0, that just means that the sequence is strictly decreasing. Okay, so that's the rule. And what that means is that option 2 is out, option 3 is out as well, because the function is strictly decreasing, not just decreasing, because it's strictly decreasing because it's getting lower and lower and will never increase, right? It will never at some point increase along the way as you increase the values of x. So it will strictly just go down. So the only correct option there left is 5, right? So the correct answer here is 5. Hopefully it makes more sense. Right. So, and if I were to represent it graphically, just for the sake of an example, just so you can understand the difference between strictly decreasing and decreasing. Let's say we have some function f of x, some arbitrary function, right? And let's say we drew it and we represented it on the x and y axis, right? X, y axis. And the function f of x is strictly decreasing if you have something like, well, I don't know, something like that. Okay. You can clearly see that as x is increasing, right? So as you're going to higher and higher values of x, you're going to lower and lower values of y. So the function is decreasing all the way down to, I don't know, as it can go as low as negative infinity, depending on how high you go in terms of x, right? So what that means is that this function is strictly decreasing. So that would be a strictly decreasing function. But now, what about, right? Let's say we have some other function g of x, and when we draw it, it's also decreasing, but it's decreasing at this rate, something like this. Once again, you can clearly see that the function is decreasing, right? Because as you go to higher and higher values of x, it still goes to lower and lower values of y, right? But in between some specific intervals of x or values of x, it's increasing first and then decreasing again to lower values, right? So that's where you could say that the function is, yes, overall it's decreasing, but there might be some intervals in terms of values of x where it's increasing. So that's just the sort of the difference between the two. Yeah, hopefully this makes it a little bit more clear. And the same applies to strictly increasing functions, right? So strictly increasing and increasing functions. So you could apply the same logic there. Right, so hopefully this helps in understanding the concept. Let's move on. So the next question, we are given a geometric series. Well, we are given a geometric series and we are asked which one of the following statements about the series is true. So we basically have to check for the divergence and or convergence of the series again. Now, remember, the general form of geometric series, right, is I don't know, some series from of the form a times r to the k, right? And k could go from depending on the series, could go from 1 or 0 depending, right? Depends on the series, but this is the general form, right? A times r to the k. Now, the way that you check if this geometric series is converging or diverging is you need to have the absolute value of r less than 1, right? So that's the rule for convergence, right? So that's the rule for convergence. The absolute value has to be less than 1, the absolute value of r. Right. So here we are not given the summation formula of the series. We are just given the first few terms, right? And using that, we have to determine what is the summation formula of the series and then check for the convergence, right? So you have two jobs. First, let's look at these, the sums that are given to us, the first few terms. So the first term is -2, the second term is 5/2, the third term is -25/8, the fourth term is 125/32. So first we need to develop the general formula of the series. So what do we observe about this series? Two things. Well, rather three things. First, you can clearly see that this is an alternating series, right? So alternating series. That's the first observation that you can make. How do you know that? Well, it's changing signs. It's going from negative. The first term is negative. The second term is positive. The third term is negative. The fourth term is positive. So it is alternating signs, right? And the second observation that you can make is that this, whatever the general form of the series looks like, it has to have a factor of 2 there, right? Because you can see that the first term has 2, the second has 2 somewhere in the denominator, the third has 8, which is also a multiple of 2, and it's same as the fourth one. So it has also 32, which is a multiple of 2 as well. So you know that whatever the general form of the series has, it has to have a term in 2 there, right? It has to have a sort of a factor of 2 in the general form, right? So it has a factor of 2. Third observation, you can see that in the numerator, we have not for the second, the first term doesn't have a term in 5, but the second term has a term in 5. The third term has a multiple of 5, which is 25. The fourth term as well, 125. So you know that the series as well, the general form of this series, has a factor of 5, right? And you might ask yourself, well, how can you conclude that when there's no factor of 5 in the first term, right? There's only a factor of 5 in the second, third, and fourth. Well, if you think about it, the first term also has a factor of 5. You can just rewrite it as -2 times 5 to the 0. That's also a factor of 5. The only difference is just that the exponent is 0 there. So it just becomes 1. But there is also a factor of 5, right? So these are the three observations that you can make. Looking at the first observation, alternating series, what that tells you is that, what it tells you is that, first of all, since the series is alternating signs, there's a factor in -1, right? You don't know what the exponent of this factor is, but there's definitely a factor in -1, such that, right? It could be to the k, it could be k plus 1. It doesn't, we don't know, right? But if you look at it, the first term is negative. What does that mean? Well, it means that when you substitute the first value of k into the general form, you get a negative factor for the first term, right? That alone tells us that if we consider that we are starting at k is equal to 0 as our first term, right? We can see that the factor has to be something like k -1 to the k plus 1, right? Such that when you substitute the first term to be k is equal to 0, you have -1 to the 1, which is a negative value, right? And then the second term is k is equal to 1. You have negative 1 to the 1 plus 1, which is 2, which is negative 1 squared, which is a positive value, right? Plus 1. So you can clearly see that it does, this factor here respects the alternating sign that we observed for the series, right? So we've already found. So if our series looks like k from k is equal to 0 to n, right? Some value n, then we have that the first term will be negative 1 to the k plus 0. So we've already established our first term, which is k plus 1, negative 1 to the k plus 1. Now let's look at the factor of 2. How is it changing as you move from the first to the second to the third to the fourth terms? Well, we can see that in the first term, negative 2 is in the, 2 is in the numerator. Let's forget about the signs first of the term because we've already accounted for that in our formula. Now, if you look at the terms, you can see that the first term has 2 in the numerator, and all the subsequent terms have 2 in the denominator, right? So what that tells you is, first of all, we have a factor of 2. We don't know what the exponent is. But now that's where you have to use a little bit of thinking here for what the exponent should be. We know that we're starting at k is equal to 0, right? So when you substitute 2, when you substitute k is equal to 0 to in the exponent of 2, you should get 2 there, right? Hopefully that makes sense. Now there are multiple combinations you could think of. Let's try with k to the 2 to the k. Well, if you substitute k is equal to 0, right? Then you have 2 to the 0, which is 1, which doesn't respect the first term there, so that doesn't work. What about k plus 1? If you substitute k plus 1, if you have k plus 1 as the exponent of 2, k is equal to 0 gives you 2 to the 0, well, rather to the 0 plus 1, which is 2 to the 1, which respects the first term. What about the second term? The second term should give you k is equal to 1. So you have 2 to the 1 plus 1, 2 squared, gives you 4, which is not what you have there, right? So what that means is this exponent doesn't work. Well, let's try something else. What about if you had negative k? Since you have terms in the negative, in the denominator, then you know that the factor of 2 has to be some sort of a negative, could be some sort of a negative exponent, right? Such that when you increase the value of k, it just gets to lower and lower values in the denominator. So let's try that. K is equal to 0 gives you 2 to the negative k, which is 2 to the negative 0, which gives you 1. Doesn't work. What if we do 1 plus negative k plus 1, sorry. What does that make us? Well, if you do that, k is equal to 0 will give you 2. K is equal to 1 will give you 0, right? Which doesn't work with the second term. So that doesn't work either. Well, how could we solve that? That's where the thinking comes in. Well, we can try different combinations. So let's try, for example, a combination where we have, well, let's rethink this. Let's look at the terms. Now, the first term, as we said, is basically just 2 to the 0. The second term is 2 to the negative 1, right? The third term is 2 to the negative 3. The fourth term is 2 to the negative 5, right? We just rewrite the factor in 2 so we can see it more clearly. You can clearly see that as you move from the first to the second to the third term, it's the exponents are decreasing at a rate of 2, right? -1 to -3 is -2. Same from -3 to -5, right, in the exponent here. Since you know that, then you know that the exponent of 2 has to have a factor in 2, right? So you know that there's a 2k there, right? Now, we know that if you leave it like that, it doesn't work for the first term. We've already checked with k. So what about if you had -2k, right? Because you have a negative exponent, but now +1. Let's try that. If k is equal to 0, you have -2 to the -2 times 0, which is 0, +1, which gives you 2 to the 1, which gives you the just my mistake, 2 to the 1 there, which gives you the first term, right? The second term is k is equal to 1. So you have 2 to the -2 times 1, which is -2, plus 1, which is -1. So you have 2 to the -1. Works for the second term. What about the third term? You have 2 to the -2 times 2, which is -4, plus 1, -3. So you have 2 to the -3, which works for the third term as well. And if you try for the fourth term, you'll see that it works as well. So we have found our term in 5. Now let's look at our term in, well, not our term in 5, but our term in 2, sorry. So let's look at our term in 5 now, because we know that we also have a factor of 5. What happens as you move from the first to the second term? You can clearly see that it's going as 5 to the 0, 5 to the 1, 5 squared, 5 cubed. So it's variating at a rate of 1. So if we try 5 to the k, what happens? Well, we have k is equal to 0, gives us 5 to the 0, 1. Works for the first term. K is equal to 1, gives us 5 to the 1, which works for the second term, and same for the other terms. So this works. So we have already found our general form. So now let's just rewrite it so we can simplify it further. Okay, so if we had to rewrite this in a general, more better looking form, k is equal to 0, because remember we have to rewrite it into the general form of a geometric series, so we are able to find what's the value of r, so we can check the convergence of the series. So let's put all the terms in k together. So we would have -1 times 2 to the -2 times 5, all to the k. And then the independent terms with no exponents in k will be -1 times 2, and that's it. So now the general form becomes the sum from k is equal to 0 to n of, if you had to rewrite this, basically -5/4 to the k multiplied by -2. So now we have the general form that we are looking for. And if we compare the both, if we compare both forms, we can see that r is equal to 5, -5/4. So immediately, if we go back to the options that are given to us, since we know that r is equal to -5/4, what options are eliminated? The first, the third, the fourth, and the fifth. So we are only left with one options really, which is option 2, which we can even confirm by just checking now for the convergence of the series. We have R. We know that for the convergence, the absolute value has to be less than 1. Well, that means that the absolute value of negative 5 over 4, which is this equal to 5 over 4, has to be less than 1, but we know that this is greater than 1, which means that the series diverge. It diverges. So what does that mean? Well, it means that the choice that we made was correct. Option number 2. Okay. So that is that for this